All attendees are in listen-only mode.
Okay, I think we are all set here, so I want to welcome everybody back to our third webinar of the year. Today we're going to be discussing electrical safety testing circuit theory. So before we begin, let me introduce our team, myself, the presenter. My name is Anthony. I'm an applications engineer here with Associated Research. We have our distinguished panelist, Jim Kennedy. He's our communications leader. He'll be fielding any questions today. If you may have some, you can also direct those to me. And Allison Oba, who is our organizer today, so she makes all this happen. Big thanks to her. A few notes to get out of the way before we get started. Please use the Q&A utility to ask Jim any questions concerning the material being presented, or any questions in general, even regarding your connectivity. If you're having audio and visual problems, Allison can get you squared away with that. Just another reminder, all our webinars are recorded and will be available usually within a day on our website. Also, they'll be available on YouTube, where we have all our webinars archived. So if you were looking for other topics, you could find those there. So again, please contact Allison at allison.oba@arisafety.com if you'd like a copy of this presentation, and she'll shoot that out to you immediately once we're done, obviously. So a quick recap on last month's webinar, which was Electrical Safety Testing 102. We did a test overview, which we'll do again a little bit today just to make sure everyone's on the same page of what these tests are. We talked about testing requirements, finding the right testing device, and what not to do when testing. Again, if you want to find that, you can head over to YouTube or our website or contact Allison. So let's talk about our webinar today, our learning objectives. We'll do a review of the electrical safety tests. We'll go over ground continuity, ground bond, Hipot testing, insulation resistance, now line leakage, and some of our features is what I want our primary topics to be. I think those might be the most complex, so we'll spend most of our time on that. And we're also going to delve into the general schematics of the electrical circuits for safety. Now, these aren't our real schematics, but just kind of the fundamental schematics of how our electrical circuits for these safety tests work, and what these standards mean when they say reverse polarity or open ground, and those type of details. And we'll finish up with Arc Detection and SmartGFI circuits. Those are two features that come on our instruments that we feel might potentially not be understood fully or even utilized in its full capacity. So let's get started with our common electrical safety tests. This is a list of all the tests we'll be going over. Again, to repeat myself, ground continuity, ground bond, dielectric withstand test, which is also known as a Hipot test, insulation resistance test, and our touch current test, which is also referred to as leakage current testing, or touch current testing. Now, I know it's early in our webinar, but I really wanted to ask this question: how confident are you in your electrical safety tests that your organization performs? And what I mean by that is, do you feel you're getting every detail right? You know, I've gone on a lot of visits where Allison should be putting that question up for you, and you should have your options of your level of confidence. I guess what I want to know is, you know, are you 100% sure that you're doing everything correctly? I know you're getting a pass result, you're getting certain number values, and you know, your auditors seeing your past results and what instruments you're using, make sure they're calibrated, but are those the actual results that you're supposed to be getting? Even though you're getting past results, are those the actual numbers that you want to be looking at? You know, there's a lot of minute details in standards that people might just gloss over because they either think they're doing it right or they're not really sure what it means, or maybe it doesn't apply to them. On a lot of, go ahead, Allison.
Hi, Anthony. So we asked the audience, I'm going to go ahead and close the poll question at the moment. We asked the audience how confident you were in the electrical safety tests that your organization performs. And as you can see, 29% of people said that they were 100% confident, 46% said that they are fairly confident, 21% say they are uncertain, and 4% say fairly unconfident. Thank you all for participating.
Okay, those are good numbers, information. Like I was saying previously, sorry about that, before I get into the ground continuity test, you know, there's a lot of visits we go on to not only demo our equipment, but make sure their testing is being, you know, appropriately done. There's a lot of details and connections, or what your actual device is, what industry you're in, you know, are you testing at the right voltages, which most people get, but it's when you get into those discrete scenarios of leakage testing, what does reverse polarity, how do I do reverse polarity, if I'm having an external AC power source, how do I properly hook that up to my DUT, you know, and I think it's important to make sure we're running those tests 100%, because, you know, even from my previous job experiencing working at a nationally recognized testing laboratory, you know, an auditor may go out there and they're not even 100% sure what, they go to a lot of different places and are seeing a lot of different tests, so which might be a good thing, you know, hey, your auditor isn't 100% sure, so you'll get your pass. But, you know, a service that we provide is we can come out to your facility, review your testing test plans, how you're setting it up, and just give you a general overview training on how to properly use your instruments and how to properly set up your tests, and just to kind of define what all these standards are and what it means when you read a certain line and you're not sure technically what it means, just to make sure that you're installing those standards correctly into your test procedures. So we appreciate that info, and it looks like, you know, a lot of people are hungry for information, which is why you're at this webinar, and we encourage you to keep following and even visit some of our archives. And again, if there's specific topics you want to talk about, please feel free to give us those ideas. So ground continuity test. Let me close this for a second. This test verifies a connection between exposed conductive parts and the ground of the power cord on the product under the test. So this, in essence, is just making sure I have a closed loop. My ground circuit, which is a safety feature, I want to make sure it's there. Make sure it's there and that current can flow from wherever it's leaking back to ground. It's a routine production line test conducted on Class 1 products. It's usually just a quick signal applied to your ground circuit, and we just want to see that return. Typically performed at current under 1 amp, even lower, to just check the ground connection is continuous. It's not to get confused with the ground bond test, which is a little bit high, a lot higher amperage and more stringent. So to clarify, we're going to run through these pretty quick, since I think we've done webinars in the past and you guys kind of have a good feel on what these tests are. But ground continuity is just to make sure it's there, you know, and is it intact? Is it a complete loop? So our ground bond test, now this is a test to verify the integrity of our ground connection between exposed metal and ground wire of the power cord. So it's the exact same wire or the same circuit, the same path that you're testing as ground continuity, but now high current is injected into the ground pin of the product's power cord, and it will flow through the entire either chassis or stud of the ground circuit. This determines if the safety ground ground wire is capable of handling excessive current flow in a case of a fault occurs and the product's installation fails. So, in the off chance that something happens where the current that should be fed to your line and a neutral, somehow a fault condition occurs and now it's all being sent to the ground, can that ground hold all that current? Or will it spill over onto the chassis of your DUT where people could start getting shocked? Here's a quick circuit, pretty basic on what the ground bond test is. I want this left side is your instrument, your testing instrument, whether it be an Omnia or a high amp. This is your adapter box or wherever you're plugging in your DUT into our instrument. Here's our transformer where we're turning either low current into high current or low voltage into high voltage. So we can see high current is injected into the ground stud of your line cord. That high current will travel through your ground circuit. Now it's not a resistor, but it's the resistance of your ground circuit. It should be a very low resistance, obviously, because we want all our fault current to run to our ground circuit. And now it's going to return back on your return connection. Now this is a Kelvin connection, meaning we have a 4-wire connection. This return path on the bottom is to hold the high current returning to the transformer, where this Kelvin path is more of where you're making your measurement. That way we can offset any resistance of your line cords. So the Kelvin method is a standard 4-wire measurement method used during a ground bond test to eliminate the inherent test lead resistance from the test results. So this Kelvin method, if you're not using it, could help you if you find yourself failing very close to that high limit. If you're superseding that high limit by a very small amount of ohms or resistance, then it's important that you're realizing, hey, I need to offset my leads because I'm getting resistance that isn't mine. That has nothing to do with my product or my DUT. That's part of my testing apparatus, so we need to offset that. I want to play some videos here to give you some examples of ground continuity, ground bond, and what the differences are. When we say fail or pass, it's kind of hard to envision that. So let me should clear up. Sorry about that. So here we have a normal wire that you would use in your ground circuit. Okay, we have our 4-wire Kelvin connection. You can see that, and first I'm going to run a continuity test, which you would assume will pass because it's a wire. I can see there's no breaks on it, and it's a complete loop. And then after that, we're going to run a ground bond test at about 30 amps. I think most people probably run theirs at 10 to 15. 30 is a bit high, but we do go up to 40 amps for special industries and special applications. So let me let this run. We'll initially run our ground continuity test. I'm not sure if the video is playing as well on your side as it is on mine. Let me rewind this. So continuity is passing, and then it immediately goes into our ground bond test at 30 amps, and you can see minimal resistance, and since your resistance level was not past your high limit, let me run this again. So here you can see the results of our last test. Our continuity passed and our ground bond passed with about 13 milliohms. So that's a very low resistance on your ground path, which is what's ideal. It's what you would want. Now here's a different type of wire that you may use on your ground circuit. apologize if these, on my side, these videos aren't playing too smoothly, but let me. So obviously continuity is going to pass again. We have a closed loop. So resistance is measured at about 120 milliohms. That's still under an ohm, which is what you want for your ground circuit. But now as it jumps to your ground bond test, you can immediately kind of start seeing some smoke, and it's even beating off the wire. If we let it test a little further, you can start seeing some redness occurring on the wire, and that jumped pretty quickly to a fire being started inside your DUT or your device. Let me run that back in case it wasn't caught very well the first time. You can kind of see smoke starting to appear, see some redness on the wire, and as you can see, the current is just too much to handle on this type of wire. So this is why the ground bond test is performed. You don't want, in case of a fault, you don't want this ground wire to break or heat up just like this occurred and start a fire inside a DUT, and who knows where that's going to go. Now the reason the test didn't stop here is because I turned my high limit to 0, so I turned it off. But normally you would have your high limit, meaning what's the highest level of resistance I will allow my ground wire to have. This was in excess of 200 milliohms, but because I turned off my high limit, my current kept outputting. So normally with your tester, if you would fail, it would never reach this point because you would have your high limit set, and once the current meets resistance that is too high, it's going to tell the device this is pretty much an open to me because I can't flow any further, or the resistance is too high, so the test has failed and your output will stop. So again, this is kind of to demonstrate what a ground bond pass and failures look like. Again, I apologize if the videos weren't playing smoothly. It might have something to do with our connection. So looking at the ground bond test as a pass, I injected high current into my ground pin. It checked what the resistance is of my ground circuit. It was at a low enough level where it was lower than my high limit and was continued on back. High current traveled back to the source, back to the transformer, while measurements were being made at this Kelvin connection. Now it's important to note that in real world testing, these won't look like two wires. They're shorted and coated in the same wire, so it'll look like one thick wire, but we want you to understand what's inside of there. It's a 4-wire Kelvin connection, which is offsetting any resistance coming from your test apparatus or your test wires, or even internal resistance of your instrument, testing instrument. So again, this left side is your tester, this right side is your DUT. Here I have my line neutral, which in this test, the ground mount test, isn't being touched. It isn't being used. Only the ground circuit is being tested. Now a fail, obviously, would be this resistance value is way too high. Meaning if a large amount of current was trying to travel through this ground circuit, it might find a different path, most likely the chassis or someone whose hand is on your DUT. This is why it's important for this ground circuit to be capable of handling high amounts of current for a decent amount of time. Most tests are usually between a second to 60 seconds. So here obviously we failed, resulting in a failure because the resistance was too high. Some other points on the ground bond test, the ground bond test is commonly considered a type test. The results of this test are displayed in ohms, obviously resistance. The ground conductor of a product must have a low enough impedance to handle any fault current, which is what we want in our ground circuits. Now, the parameters on your ground bond test will vary standard to standard. Some test at 5 amps, 10 amps, 15, all the way up to 60 amps. You guys, The onus is on you to find the right instrument and comply to that standard, but this is what our apps team is here for, to answer those questions for you, to kind of lead you into the right instrument to make sure you're meeting those standards. Perfect example is UL 60950 in IT equipment calls out for the test current to be twice the fuse rating on the product or twice the current rating of the circuit under test. So, you know, fuses can go up from 10 to 20 amps, so your testing could be at 20 to 40. Also, some standards calls out for the test voltage of a ground bond test to not exceed 3 volts and the duration of the test to be 120 seconds. There's some ground bond tests that want your voltage to be at 3 volts. You know, so it all depends on what standard you're testing to. Test current could be an AC or DC based on the product as well. So these are all parameters that are important to find in the standard you're testing to. Now our Hipot test, which is most popular test, by that I mean most ran, most performed, also call it a dielectric withstand test. It's used to determine whether the insulation of a product is able to withstand an overvoltage condition for a period of time without breaking. So again, just like your ground bond test, in the fault condition where your current is now no longer going to your line of neutral and all leaking to your ground circuit, what happens if you're no longer running at 120 volts and something happens where you're at an overvoltage condition? Can that insulation withstand that electric field, or will current start to flow through your insulation, again causing another situation where if my hand's on your DUT, that current leaking through your insulation will start flowing through me, which is a dangerous situation. So this test verifies that the insulation of a product is capable of protecting the user from any leakage currents as a result of an electrical fault within the product. I think we're all pretty accustomed to the Hipot test. It can be a type test or a routine test. It's used to detect possible defects in the design of a product and workmanship defects such as inadequate creepage and clearance distances. What's that mean? So let's look at this diagram here, or a schematic if you say. You see two capacitors here. I don't want that to be misleading. When I short my line of neutral, as I have here, and I apply high voltage to it. Now when I say I apply high voltage to it, voltage is always referenced by 2 points, right? So my line of neutral has now become 1 point, my high side, my red, my hot side. And now my return, or my reference, my zero, my low, is on my ground circuit. So you've kind of simulated a capacitor, right? 2 plates holding a charge. So that's what these capacitors are. It's kind of just simulating what a Hipot test does to your line neutral and your ground circuit. So technically this capacitor here is everywhere, from all around this whole opening here, wherever that electric field is being exposed to between those 2 points. So this ground signifies that I'm shorted to ground here. My return is to ground. Now let's play a video. Hopefully it plays a little bit better. So here you can see I'm using a different connection now. I'm using my high voltage lead as opposed to my 2-wire current output lead, but I'm using the same return. Now you can use the same return on your Hipot and your ground bond. Now this one might be overkill because this one's rated for high current, but in essence it does the same job. Now you can't use all returns with ground bond tests. It needs to be rated for high current. So here we're applying high voltage to, my sample is my TVB2 box. This is a test verification box. It's kind of required for you to do verification testing. It doesn't have to be our TVB2, but as long as it meets the criteria set by your UL or ETL auditor, that you're running verification testing daily or week, whatever they whatever your requirement is. So this is our TVB2 box. It's a good way for me to simulate a pass and a fail. This is a contrived load box. You know, I know what the resistance is on each of these channels, so using specific parameters, I can verify that my pass and my fail detectors are properly running. And in essence, I'm verifying that my instrument is properly running. So here I'm switching sides to my pass side. Here run my pass ground bond test at 1.24 kilovolts. My current was at about 0.620 milliamps. That's fair for a pass. Now, if I want to switch over to my fail side on my TVB2, you can see I'm leaking more than nearly 10 milliamps, I'm sorry, which is more than enough to hurt somebody. I know this through experience. So this TVB2 box is a great way to verify your instrument's running, but for our needs right now, I'm just showing you what a Hipot test looks like when you're running it. Okay, so let's go back to our circuits so we can kind of explain more of what's happening. So here's our pass. You can kind of disregard the moving green dashes because really when your Hipot passes, there's nothing moving. I do have an electric field there, but ideally in a pass, no current is flowing through this capacitor here. Capacitor, the space here being your insulation. So right now my electric field is there and is being applied to your DUT, but your insulation is holding up. It doesn't matter how strong that electric field is, no electrons are breaking through or no current is leaking through your insulation. So that's good insulation, that's a good pass. A fail is when that electric field is too strong, that difference of potential is too strong that electrons or current starts breaking through your insulation and it's now leaking to ground. Now what's leaking to ground mean? That means it's probably also going to start leaking on your chassis, especially if, you know, I'm low impedance, you know, a path of least resistance. This is why we perform our Hipot tests. Hopefully that clarified that. Some more points. Leakage current is present in every product to some degree. Every product is going to leak, but there's a certain level of current where I can't even perceive. I can be getting current flowing through me and I'm not perceiving it. It's only until you get to that level where I'm starting to, perception occurs, danger occurs, harm can occur to a person. I mean, we all naturally have current flowing through us. That's how our eyes blink and our hands move. But once you get to a certain level, that's when it becomes dangerous, and that's what the Hipot test is there to test for. Result is displayed in milliamps or microamps, ideally, depending on the test type. This test is performed on both Class 1 and Class 2 products. You might ask, how do you test on the Class 2 products? I'm sure the question comes up a lot, but there's different methods from wrapping in foil to different type of liquid materials you can apply. You sometimes, depending on your budget, you can get really creative. Test voltage and trip settings must be specified by the manufacturer in accordance with the safety standard. For the most part, I think the general rule that everyone knows is what your product is rated at times 2 plus 1,000 volts. That's just kind of a worst case scenario of, I know I'm running at 120, you know, let's see what happens at 1240. If my device can take 1240, I'm fairly confident at 120 nothing's breaking through my insulation. Let's move to our IR test. Again, I'll move a little bit quicker to try to get through these because I know you've attended some webinars discussing these. It's very similar to your DC dielectric withstand test. The only difference is now your result is in resistance. I'm no longer telling you how much current is leaking through your insulation. I'm now telling you the specific value of your insulation's resistance. You know, is it 10 mega ohms, 5 mega ohms? So that's kind of the difference between your DCW, DC withstand test, and your IR test, insulation resistance test. And most standards kind of specify test voltage at 500 or 1,000 volts, because really the voltage isn't too important because you're just identifying what the resistance value is. Obviously, high insulation resistance value indicates good insulation. Like other electrical safety tests, test parameters vary. Like I just said, 500 or 1,000 volts. You know, for example, EN 60204-1, safety of machinery, specifies at 500 volts DC, and your resistance shall not be less than 1 mega ohm. So what's that mean? That means your insulation needs high resistance, and it cannot dip under 1 mega ohm, or it's considered a failure. Now your leakage current test, this is where we have the most questions, and to be honest, it's really tough to be an expert on leakage current tests because there's so many different types of standards, and they're performed in such different ways. But when it comes to, you know, medical device and other types of electronics devices, you know, we've become pretty educated on it. So, you know, always feel free to reach out to our apps group if you're uncertain if you're properly testing your parameters, your fault conditions, which we'll get into further. Line leakage test is performed on electrical products to measure the leakage current which could flow through a person while the product is operating. So that's the distinct difference from this test and all the other tests. Your product will be powered on. I want to know if when your product is out in the field, or better yet in a consumer's home, and it's powered on, how much current is leaking naturally on its own. You know, so we use a measuring device to simulate the impedance of a human under different conditions depending on the application of the product. So this is why leakage current testing is huge in the medical field, because it's one of the few applications where electrical devices are literally attached to us. So any current flowing through it won't depend on if I'm touching it or if I'm grabbing it or if I'm walking by. Like, it's connected to me. I'm on it. You know, stuff like watches, new electronic watches, you know. Wearable technology is where leakage current testing is most prevalent. So the test is run under both normal single fault conditions and reverse polarity. Again, this is when I was referring to, I'm not sure a lot of people are certain that they're 100% running it right. These fault conditions can get very confusing, you know. Plus, being powered at 110% of rated voltages, you know, are people using sources to power up their devices, or are they just plugging into the wall, or are they just using a transformer to try to get 110%? You know, how can you be certain it's 110%? So this is a little diagram or a circuit schematic to kind of, right now looking at it might be confusing, but hopefully by the time we're done with this you'll understand what all these fault conditions are. So let's establish where we're at. This is the line neutral of where your DUT is being powered up. Okay, it can be referred to as your T1 in most standards. So this is just, you can think of this line neutral as the power coming from the wall when you plug in your device, but it's going to be at 110% of your rated voltage. So if you're rated at 120, you must be testing at 132. So let's follow our line. This is my line. Ideally, it would come into my DUT and come back out to neutral, right? So we see we have a switch right here on my line, that if this switch was open, line now kind of becomes neutral. Same thing with my neutral here. I have a switch here that if this was to open, I've just shorted my neutral to my line. So that's a quick way to reverse polarity. You know, it's interesting, you know, to think about what happens if you're running and then boom, I quickly switch over to line neutral. Is there an increase in leakage current? You know, disconnect, leakage is running, you disconnect it, it still wants to run. Is it going to start trying to pull a lot more current for that momentary disconnection? So that's reverse polarity. That's one of your fault conditions that you need to meet. Now, again, just to clarify, that's this switch right here and this switch right here being open. Open, open. I've now crossed my line of neutral. Another switch I have is right here, this S1, which can be opened, meaning open neutral. So what happens if my line is connected, I have current flowing through my device, oh, I apologize, and my neutral suddenly opens. These are just random fault conditions that we want to know that may occur. Is it likely that they'll occur? Probably not. But when it does occur, I want to know how much current will be leaking in my device, because it's all about safety. You know, it only takes that fault condition to occur once. If you have no idea what happens to your product when that fault condition occurs, and now if you're a medical, obviously if you're a medical device company and you've just shocked someone, there's a large amount of liability, and we just don't want to enter those what ifs. And now my third condition, which I think from my experience, what I've noticed a lot of people aren't maybe realizing to do, is your ground circuit. You see my ground pin here. This is my ground circuit going to my MD. You have to open and close that. You know, if your ground is closed, you're not going to see a lot of leakage current because it's all flowing to ground. Once you open your ground and all that leakage current no longer has that path to go to, it's going to go to the meter, our measuring device that we have in there. That's when you're getting your true values of what your leakage current values are during these fault conditions. So I just stated 3 faults. You know, 2 to the third, that's 8 combinations. 8 combinations that you need to be testing. Now when ground is closed, I've seen that you can kind of excuse those or not do those, because for the most part you should be seeing 0 leakage when your ground circuit is closed or connected. But once you open that, now all that current is flowing to the measuring device. That's when you're getting those real values that you want to know. So the measuring device that you're using, I know in an Omnia 2, which is kind of the instrument which predominantly dominates the leakage current testing industry when it comes to AR, we have a plethora of different measuring devices, but they're really simple components. You know, 2 resistors and a capacitor. It's just there to guarantee a certain resistance range that's simulating the human body impedance. So there's nothing really too technical about measuring devices, but the values that come across that are very important, because that's what will be flowing to consumers or patients who are connected to your devices. So again, a measuring device is usually just a couple little components on a PCB that you can actually make yourself. We've given you the convenience of giving you about 8 to 10 different standards, different measuring device that they call out for, so you can already find those in your instrument. And we also have an empty circuit board that if you're testing to a different standard, you can kind of build your own. So just to go back, I want to make sure we've clarified the fault conditions, reverse polarity, open neutral, open ground. They should all be getting done, and they should all be getting done in all those 8 combinations. So before we get into these features, I kind of wanted to ask a poll question. Is everyone using Arc Detection or SmartGFI? I think, you know, our engineering staff has come up with a lot of great features through their high-level technical thinking that maybe I haven't done a great job explaining what they do, and so sometimes people will choose not to use them since they don't understand them. And so that's why we're having this webinar, because we want to make sure you fully understand the capabilities of your instruments. And once you know them, then you can make a sound decision of, I do need to use them or I don't need to use them. So Allison will open that poll up and we can kind of discuss the results.
All right, all. Thank you so much for voting in our poll question today. So we asked if you use either the Arc Detection or SmartGFI features of your instruments. 13% use Arc Detection, 4% use SmartGFI, 9% use both Arc Detection and SmartGFI, 30% do not use those features, and 43% are interested in learning more about these features. Thank you all so much for participating.
Okay, that's great feedback. For those 43%, we're hoping to answer those questions in this next section of our webinar. So let's talk a little bit about arc detection. Arcing is a momentary partial discharge due to the intense concentration of a high voltage electric field across a dielectric. That's a mouthful that I'm sure people could read 10 times and still not be sure what it is. You know, when there's a high electric field or voltage on an area, or for our applications insulation, you know, there can become this luminous kind of corona, we call it. And with this corona, you know, the air around insulation can become ionized, and there's a quick spike, a quick discharge, which isn't exactly a breakdown, but it can give you insight into potential issues with your insulation. So in Hipot testing, the dielectric is the insulation of the device under test. Arcing produces momentary spikes in this nominal leakage current waveform. We'll have some graphs on the next slide to kind of explain this. Arcing is different from dielectric breakdown. Dielectric breakdown, we're getting into a large rise of current where you're leaking a certain amount of current, and now I'm seeing a gradual but large increase in the amount of leakage flowing through your insulation, where now I've established there's a hole in your insulation, there's some sort of path from line to ground, or line neutral to ground, between your insulation, where now I can call it a breakdown. A breakdown has occurred, and if I'm applying this much high voltage, a large amount of current, too much current, will be flowing through your insulation, which creates a dangerous situation. Arc failure does not necessarily mean Hipot failure. Arc detection provides useful information about the product's insulation. So again, just to kind of read that, arcing is a momentary partial discharge. So an electric field has a lot of effects on insulation or just air in general. So when those ions on your insulation, those molecules, they start getting ionized, it can almost cause like a lightning strike, like a mini lightning strike, a mini discharge, where, you know, lightning isn't constant. You know, it's cool if we can get lightning on camera, but it's pretty hard because it's pretty quick, as opposed to leakage, where you'd be able to see leakage flowing into your insulation if your output wasn't shut off. Once we see breakdown, obviously your high voltage is shut off on your instruments, but that's kind of a way to think about it. So arc detection, here you have your wave, low frequency wave. Now that arcing is usually caused at peaks, obviously at high voltage. When the voltage is at its highest, you start getting these spikes, these high frequency peaks caused by the ionization of those molecules, or the proper terminology is corona. So it's important to note, is corona building up on my insulation when I'm running Hipot tests? That can give you insight into the quality of your insulation. Does it mean you're failing? No, it absolutely does not mean you're failing. So if you're not using arc detection, it's fine and it's understandable. It's just a feature that gives you more data for you to examine to identify the quality of your insulation. And like I said, 10 microseconds. So this high frequency discharge occurs in 10 microseconds. So it's something that probably isn't going to harm a consumer like a Hipot breakdown would, but it can lead to breakdown down the line perhaps if you were Hipotting over and over and over the same device, which again isn't really likely, but just more information, more data for you to analyze when trying to understand the quality of your insulation. So how is arc detection handled? So using a high pass filter will clear out the normal low frequency wave. A high pass filter on 10 kilohertz. So now we've isolated that discharge. We've isolated that quick arc. Now that arc, which has occurred, is now going to, using a comparator, is now going to be compared to the level you've set your arc detection sensitivity on. So if you have an instrument with arc detection, you also have the ability to adjust its sensitivity from 1 to 9. So if you're trying to understand, am I getting less corona, more corona during the RD phase of your development, you will set your sensitivity to 1 or 9 depending on what type of information you want to get, and you'll be able to compare, did this arc get stronger or is it the same? Is my insulation getting weaker because the arc is getting higher? Or if I run this test 10 times, is the sensitivity the same? You know, so I can set my sensitivity level to 5. If it's not going off, if I'm getting this corona and I'm getting these arcs, but the high pass filter, or the comparator, I'm sorry, is not seeing the arc at a higher level than what we set 5 at, and you run that test, you know, every week, and you're still not failing at 5, then you can kind of have peace of mind that, like, okay, my insulation does arc a bit, and we do see corona, but it's consistent, and it's not weakening my insulation. That's kind of a way to use your sensitivity level adjustments to kind of have a control, to have a barometer of what this arcing is doing to your insulation. So in normal use, you know, we see an arc, we send it through our high pass filter, we're now comparing it to what your sensitivity level was set to, and if it exceeds that, we're going to send it to our CPU to fail it with arc detection. Arc fail is what the message would say on your instrument. So again, we don't want to confuse this with a failure of breakdown, which is what standards call out for. This is just a way for you to kind of check yourself on the quality of your insulation. So if you have it off, it's not the biggest deal because arc failures aren't called out in the standards that I've come across. If you know of any that do, I'd appreciate that info, and we could do some research on that. But this is how our instruments detect arc occurrences. So now let's get into our SmartGFI. So the SmartGFI is actually a patented safety feature in all associated research high voltage safety testers. Let me turn that off, sorry about that. The Associated Research SmartGFI circuit will shut down high voltage if excess leakage is detected through the ground circuit. So this is a high-speed shutdown. In less than a millisecond, high voltage will shut off or be disabled when current is leaking to the ground circuit. It's an active circuit which monitors the configuration of the return connection and automatically sets itself accordingly. So what's smart about this is it will know if your DUT is connected to a floating ground or an actual ground. Let's look at I think some of these words we've probably heard a lot, and when explaining to customers, we've said this before, but it's better to kind of see a diagram of what's actually happening. So here we have our guy, we'll call him Adam, and on the left side we'll have our transformer. So this is our high voltage transformer inside your Hipot tester. It's turning, technically there should be more loops here because it's turning about 120 volts into whatever your testing voltage is, right? Up to 1.24 kilovolts. So high voltage is set on our line of neutral. Let's assume he's not touching high voltage at the moment, and here's our return. So what happens is if there's leakage current but perhaps not breakdown, that leakage current is obviously going to return from here to ground straight back to the transformer, right? Now the issue that comes up is this transformer knows how much, oops, sorry about that. This transformer knows how much current is being put out or how much current is missing, or they know the total value of the current that this DUT has just pulled from me, whether it be from normal use or from leakage to ground. It knows that it should see that much in the return. So the GFI kicks in when that comparator, that those values are off. When those values are off, your instrument or the SmartGFI knows that, whoa, there's current that's missing right now. And the most likely scenario is that that current has probably found a new path. And what that new path is most likely a user or a consumer, or most likely your test operator, which is using your instrument, you know, or it found some other path. Regardless, it's a dangerous situation, so that GFI is there as a safety procedure. It's got nothing to do with, you know, standards or what you're testing to. This is purely to maintain a safe atmosphere for your operator. So we have our return ground sensor and our ground fault current sensor. So what that is saying is the current that we lost that went through Adam here and now returned to Earth, your isolated transformer is going to see that current returned through ground, and it's going to set off your GFI, so your ground fault current sensor. So it's a little bit complex on how it works, but current is missing. That missing current returns through ground. That's what triggers the GFI to activate. So your GFI is on default when you get your instrument right out the box. Your GFI is on. Now, a lot of people do turn it off because they just know that their products are naturally leaky. You know, there's just other paths on your DUT or on your product where leakage current might flow through or flow to. So GFI might just hinder your testing because you're constantly going to get GFI fault where you can't complete a test. So this is why we do see some of our customers turning off or disabling GFI. We don't recommend that. You know, I guess if someone tells you, hey, my product is naturally leaky, well then we'd say, well, you know, make it not naturally leaky, you know, because that's still current that can be flowing to places you don't know. And if someone touches the right spot, or the wrong spot I should say, that current can flow to Adam or the user. Before, I wanted to show a video here on this is kind of an obnoxious example of arcing, but what we have here is your normal power plant where current is flowing through these conductive materials. Now, current wants to keep moving where it's going. You know, it's found a path to ground, it's found highly conductive metal, I'm going to flow on this. Now, when you open those and separate it, if that voltage is strong enough, if that electric field is strong enough, that current doesn't care. I don't care if you've just eliminated my path, I'm going to create my own. And that's kind of high frequency discharges. It's not quite, this is kind of a macro example of an arc, but for you to kind of understand the concept, you know, I've just opened up that this is insulation. All this air is insulation, right? But the voltage is so strong that that current is going to continue to flow. Now, normally in an arc, it would be a quick shot, something like that, a quick shot that is for the most part not detectable as a breakdown. But this is why it's important to use arc detection to make sure that your insulation, the quality of your insulation is up to par with what you're trying to do and what standards you're trying to meet. I think content-wise, that'll do it for today. I do want to open it up to questions because I know this was some important topics here that I want to make sure everyone walks away with all their questions answered, as well as let you know that you can reach out to us. If you don't want to ask the questions here, feel free to send me an email, and if it's a question I can't answer, I'll make sure I'll go to our more qualified engineers to get proper solution for your questions or any test setup issues you may have. So I'll leave it to Allison or Jim to see if we've had any questions that need to be answered at this current moment. Okay, I'm gonna, as I look in the text box, I don't see too many questions at the moment. Let's see. Here we go. See, we got a lot of good spell check questions. Okay. So here's a good question. Arc detection, can it be used to contribute to life cycle estimates for products and installation? So that's a good question. Absolutely. Arc detection, you need to establish your base. I would set my arc detector level to 9, being most sensitive, right? If you're failing during Hipot at 9, I mean, if you're failing with arc detection, arc fail at 9, you know for sure there's arcing going on. So at your normal Hipot test, your arc levels are set to most sensitive. I may need to check if it's a 1 or 9, most sensitive. I'm pretty sure it's 9 though. You need to, through the life of your product, since I'm assuming you're going to be in the R&D type testing portion of your product development, you know, you've established that you're arcing at its most sensitive level. Now you've established a foundation, so keep Hipotting that test, 60-second Hipots, and you know, it's actually reversed. Put it at not the most sensitive, the least sensitive. Are you arcing at the least sensitive? You're probably not. Hipot for 60 seconds, change your arc to 2. Are you failing arc then? If you're not, Hipot for another 60 seconds. You can do this weekly, you can do this daily, or you can do this till fail, right? So Hipot for 60 seconds, arc detect at 1, no. Hipot again until you get that arc detect fail, and now you can kind of start getting some points to establish a trajectory of the life cycle of your installation. That's the method I would use when trying to establish life cycle estimates. But that's a great question, Carol, and if there's any other methods or ideas, we'll make sure to email you. Let's see, Nelson's good. And Abel, do you think UL 471 will use your current leakage tester instead of the so that's UL 471, no standards call out what tester you can and can't use. You know, as long as those instruments meet the requirements, whether it be, you know, transformer requirements or current limit requirements, you should be able to choose any instrument you want. Personally, I have worked at UL before, and there is no specific instrument that they use. You know, I've used an AR instrument, I've used other instruments, and what matters more is the results and that the instrument is calibrated. And I just want to make sure, you know, it's known that their instrument must be calibrated, it must meet standards, and if you're uncertain about any of those, you can kind of check the specs of your instruments for other companies, or you can call the apps teams, which we can kind of sift through your standard to make sure that our instrument is fit for your standards. We'll never sell you an instrument saying we're not sure if it meets your standard, but if you need a Hipot tester, ground bond tester, here you go, good luck. We'll make sure that the instrument is good for the standard you're testing to. Again, you can contact application support through email. My email personally is anthony.arroyo, A-R-R-O-Y-O, @arisafety.com. So if you want to direct message me any of your questions or any other comments or even feedback, you know, I think if maybe I should have shut off my camera, might have showed the videos a little bit better. That's great feedback for next time. And again, Allison will email you the slides if you ask for them. Please join us again for our next webinar in about a month. Allison will be sending you emails with what the topic will be and when it will be. And so if there's no further questions, I just want to thank everyone for participating today. I hope some answers were given, some questions were answered, and we'll see you next month. Okay, thank you.